Time is probably the only global standard. Today we will look into how we can create extremely precise timing, and we see how we can get a precision time and frequency reference for our lab. Grüezi YouTubers, here is the guy with the Swiss accent, with a new episode and fresh ideas around sensors and microcontrollers. Remember, if you subscribe, you will always sit in the first row. Precise timing is more critical than most of us know. We probably know basic timing like planning a working video conference across time zone, for example, or catch your next flight if you intend to fly soon. All these tasks based on agreed timing. But there is much more. Therefore, in this video we will look at the typical applications of precise timing. Look at the various ways of creating an oscillating signal, from unprecise to extremely precise. Look at the frequency precision and stability they can reach and how it compares with what we need or want for our 10 GHz experiment. Look at the devices that can create extremely precise frequency based on GPS signals. They are more precise than rubidium standards, for example. Look at how we can stabilize our standard lab instruments. Use a cheap GPS receiver as an exact frequency generator. To solve the issue of scheduling meetings or to catch a plane, we can use NTP Time or DCF77 clocks. Two services that deliver very precise time information in the long run. I made a few videos on how to use NTP and even how to create your own DCF77 transmitter. Such timers are long-term stable, because we want that our clock is precise also for the next years. Their short-term accuracy is rather low, maybe in the 100 milliseconds or so. Smartphones using GSM, LTE or 5G need precision timing to synchronize all communications and to enable many smartphones to use the same tower and switch from one tower to the next without any interruption. Here we also need short-term accuracy. And this is very good for makers, as we will later see. The most critical mainstream application of time, however, is GPS navigation. Because the satellites cannot use a tape measure to estimate the distance to your location, they have to use something else. They use the speed of light and measure the time radio waves travel from various satellites to your GPS receiver. Light travels with a speed of around 300,000 kilometers per second. It takes roughly 1 nanosecond to travel 1 foot or 30 centimeters. So we have to be able to measure quite precisely. But our GPS receivers should be cheap, therefore they cannot have a precision clock. This is why the satellites have to synchronize times and transmit this information to the GPS receiver. Because all those signals are in sync, the receiver only has to measure the difference, which can be done cheaply, as we all know. The GPS satellites, on the other hand, all have to carry atomic clocks and synchronize them daily with even more precise atomic clocks on Earth. This is where the hack starts. We can hijack this exact timing into our lab in the basement and use it for our purpose. Again, a cool hack where we can save a ton of money. But let's first start with creating waves, the basis for all timing. The simplest oscillator is an amplifier and a delay. We all know that it is easy to build. Put your microphone in front of a loudspeaker and usually you will hear a loud sound of various frequencies. This is because the microphone catches a slightly delayed version of the sound of the loudspeaker and the amplifier feeds it back to the loudspeaker. And ready is the oscillator. Not on a very precise or stable frequency, of course. This principle was also used by the small AM or FM transmitters we built when we were young. They use a transistor, a capacitor and an inductor to create precisely the same. an amplified feedback loop. Also here, the frequency is not very predictable and also not stable because temperature and other changes influence the values of the parts and therefore the frequency. Fortunately, FM receivers can adjust their frequency to a certain degree, so they worked. Then came the Quartz resonators. They came into my life when I started with CB radio. For each channel I had to buy a different one. Expensive for the time, so I still remember. It is a mechanical part that oscillates on one base frequency. Interestingly, it can mechanically oscillate up to a few megahertz. Most other mechanical oscillators are on much lower frequencies. And quartzes have incredibly high Q factors, which means that such oscillators resonate with a very low bandwidth. Their maximum frequencies are at maybe 100 or 200 megahertz. But we learned in the last satellite video how we could multiply frequencies by using a PLL. Unfortunately, they changed their resonance frequency with temperature and age. According to Wikipedia, a typical value is 10 to the minus 5 or more and also 10 to 20 ppm per year. What does this mean? If we have a frequency of 25 MHz, we have a deviation of 1250 Hz. Aging not included. Not a lot, you might think. If we boost the frequency up to 10 GHz for our satellite, we get 500 kHz deviation. What sounded great on 27 MHz CB radio when I was young sounds horribly wrong for an adult with other needs. This is what nobody told me when I was 16. I only thought, as an adult, I will be able to drive a car, to earn lots of money, and to have lots of sex. Nobody told me that life becomes much more difficult too. Anyway, I'm now adult enough to solve this problem. We still have some arrows in the quiver, as we say here. The next are the so-called TCXOs, temperature compensated crystal oscillators. As the name says, they measure temperature and make some adjustments to their resonating frequency. Important, they look similar to the standard quartz resonators and are also soldered on the PCB. They just have 4 pins instead of 2. The trick of measuring temperature and do something against it is a well-known concept in electronics and also here works fine. We can buy TCXOs for our SDR receiver, for example, with 0.5 ppm. And they do not cost an arm and a leg. If we do the calculation for 10 GHz, we get 10 kHz. Much better. But still not enough for my purpose. This is why I desoldered the TCXO in the Adam Pluto SDR receiver and changed it for a small IPX connector to connect an external, more precise reference. The Hack RF, for example, already has such an input connector as most other time-based instruments. The discussion about temperature changes leads us to the next level of precision. If we put our quartz oscillator into an isolated case and heat it to a stable temperature, which is always higher than ambient temperature, it becomes much more precise, because we removed the biggest enemy of instability, temperature change. These oscillators are called oven-controlled crystal oscillators, short OCXOs. As you see here, they are better than TCXOs. But they consume a lot of energy and are much bigger compared with the two principles before. We also leave now the ppm world because our numbers became too small. At 10 GHz we get now around 300 Hz stability across the whole temperature range. Cool. Or should I say hot? Because they run at more than 70 degrees centigrade inside the case. But this is still not sufficient for me, especially one aspect. You can trim these OCXOs to be very precise, but you have to calibrate them from time to time, which easily can cost you the arm and the leg we saved before. How can we avoid this expensive calibration? We can discipline such an OCXO with a more precise standard. We still keep the short-term stability of the OCXO, but add a long-term guard who makes sure that over the next few million years it will not change its frequency. But how is this done? The principle is the same as we saw with the PLL. We compare the phases of the exact reference with the phases of the OCXO. If the frequency starts to become a little bit different, the phase reacts immediately, as we see here. If we measure this shift and create a signal, we can adjust the frequency of the OCXO by a very, very tiny step. We discipline the OCXO to the more precise time. Because after these adjustments, the OCXO is already nearly precise, it can run for some time without being disciplined. Similarly to the approach the police uses to stabilize speeding. It is sufficient for most of us if we are disciplined from time to time only, and we keep our speeds in acceptable limits. Another advantage of such OCXOs is that they have a low phase noise, which means they have a very high short-term frequency stability, which is very suitable for RF applications. But what are the possibilities to get such a precise time signal which can be used to discipline our already precise OCXOs? There are a few extremely precise timers in the world. For example, this cesium clock in Switzerland only has an uncertainty of 1 second in 30 million years. Now we are at precisions for adults. Unfortunately, this clock looks clumsy and expensive. But fortunately, we can use another atom which is less precise, but it can build smaller and cheaper clocks. Rubidium. You can get a new rubidium standard for your lab for $2,000 or so. And if you are lucky, you get a used one on eBay for less. Or you go the more straightforward way as I do. Use GPS satellites. As shown before, GPS needs extremely precise timing to measure distances. If we use its signal to discipline a TCXO or an OCXO, we get a precision frequency standard, as we see here, up to 10 to the minus 11. We most probably will not get to this number, but we should get to at least to the rubidium standard, which is okay. If we do the calculations here, we get 10 Hz on 10 GHz. If on a future Sunday evening I select 10.489740 MHz for the Swiss round, my frequency should be 10 Hz away, without calibration for the next few thousand years. Enough for the girls I go out with. And its name? GPS Disciplined Oscillator, short GPSDO. With such a reference and a distribution box, your lab has a precise base for all your work. Atomic clock precision for $235, including shipping. And because your instruments are now exact, you can use them to check all your other devices if their frequency is precise. But now to the tests. I start with the standard Quartz of the satellite receiver I plan to use for my project. It should resonate at 25 MHz, but of course it is not. To visualize it, I put its frequency on the yellow channel and a GPSDO reference signal on the blue one. We see that the frequencies are very different. Please do not call me a dentist, but I will extract this quartz in my next satellite video. Next is this 10 MHz oven-controlled oscillator, which is built in this distribution box. Fortunately, 10 MHz is the standard for external reference signals. So I can use it to feed my signal generator, my counter, and my spectrum analyzer. I was not aware that the distribution box also has an OCXO when I ordered it, but now it's here. You see also something typical. These Chinese devices use used OCXOs from good suppliers like CTS. Its datasheet says frequency stability across the whole temperature range is ±5 ppb. ppb is parts per billion, or 10 to the minus 9, which is similar to the number mentioned on Wikipedia. But it has a much higher initial difference. And also during the first year it moves a bit. So it is exceptionally stable but not precise. Do you remember when I said it helps us that all GPS antennas have to have such OCXOs? Here is the proof. The chance this oscillator has had a first life in a cellular tower is very high. Let's compare its signal with a GPSDO. Again, blue is the GPSDO and yellow the oven-controlled oscillator. We see that both frequencies are nearly the same, and only its phase moves a little. Already quite encouraging compared with the standard Quartz from before. And now the GPSDO. This one came with a distribution box. Let's take it apart. It also has a second-hand OCXO from another manufacturer. You see, the PCB can host many different makes. I assume they buy whatever brand they get and mount them to the boards. On the bottom we see that it is not a simple design. Here is the GPS and here an Altera CPLD. It creates a 10 MHz sine wave and you cannot change its frequency. The other GPSDO is from Leo Bodnar. Its frequency is programmable and it has two outputs where you can choose different frequencies. Its output signals are square wave-ish, as we see here. I plan to use this one for my satellite project because I need 25 MHz to replace the crystal oscillator, for example. It uses a TCXO instead of an OCXO and therefore is smaller. But we can have it simpler. We can use such a GPS receiver module without any other oscillator. With factory settings, the Ublox GPS module creates 1 pulse per second at pin time pulse. On the Neo 6, 7 or 8, this is pin number 3 of the module. If you want to use your module for this purpose, maybe you buy one where the pin is available at the header. I have here an old Neo 6 and had to solder a wire directly to the pin of the module. It is possible, but only with a small soldering tip. If we connect the module via an FTDI adapter to our PC, we can start U-Center, connect to our GPS module and go to View Configuration View. Here we find TP5 and we see this 1 second definition. Change to frequency and enter the requested frequency, which has to be below 24 MHz. Here we have another section. The top one is for free running and this one is for locked to the GPS signal. If we change the first one to 10 MHz and 50% duty cycle and send it to the module, we see a 10 MHz signal at the time pulse pin, even if we do not connect the GPS receiver to an antenna. If we connect an antenna and it gets a satellite fix, then it produces the frequency defined here. Usually you choose both the same. Like that, the module always generates the same frequency. Much more precise with a GPS fix, of course. In the end, you have to store it in the non-volatile memory of the chip, that it is there after power down. Summarized, we got an overview of precision timing applications. We compared different ways of creating stable frequencies, starting with a standard crystal oscillator, continuing with temperature-controlled TCXOs to oven-controlled OCXOs. Each step up increased precision and got us independence of temperature changes. But it did not solve the problem of frequency calibration. Only disciplined oscillators provide absolute exact frequencies, at least for a typical maker lab. We can buy a rubidium reference module or, as I did, a GPS disciplined oscillator. The Chinese GPSDOs reuse OCXOs from professional devices. Like that, you get a good quality signal for a low price. You get GPSDOs producing a single, usually 10 MHz signal, or programmable ones producing different frequencies. Particularly, the single frequency standards create sine waves without harmonics. Other GPSDOs, particularly the ones with programmable frequencies, create square waves with lots of harmonics. We also used a cheap GPS receiver as an exact frequency generator. Such a GPSDO once forever solves the problem of measuring exact frequencies in our lab. And it is the base for a stable communication for our 10 GHz satellite project. This was all for today. As always, you find the relevant links in the description. I hope this video was useful or at least interesting for you. If true, please consider supporting the channel to secure its future existence. Thank you. Bye.